The flight tracking systems across northern Europe showed normal operations. On March 14, 2024, air traffic controllers in Vilnius, Helsinki, and Warsaw monitored their screens with the same calm professionalism they'd maintained for years. Commercial aviation over the Baltic Sea region moved in its familiar choreography, departures climbing, arrivals descending, transit routes threading between controlled airspaces. Nothing indicated that beneath this visible order, navigation systems were beginning to drift. The anomaly began as something too small to trigger alarms. At 04:17 UTC, a Scandinavian Airlines flight reported a minor GPS discrepancy during its approach to Tallinn. The deviation measured 340 meters, well within acceptable parameters for instrument cross-check procedures. The crew switched to secondary navigation, completed their approach using ground-based systems, and filed a routine maintenance note. 2 controllers noted the report. Neither escalated it. By the time the aircraft taxied to its gate, the incident had already disappeared into the noise of daily operations. But the drift was spreading. Over the next 6 hours, similar reports began accumulating across the region. A cargo flight over the Gulf of Finland noticed coordinates shifting during cruise. A medical evacuation helicopter near Gdansk experienced brief GPS instability. A military transport approaching a Mari airbase logged navigation inconsistencies that resolved within minutes. Each incident seemed isolated. Each fell below the threshold for immediate action. The systems returned to normal quickly enough that crews attributed the problems to atmospheric interference or equipment aging. At 11:43 UTC, the pattern became impossible to ignore. 17 aircraft reported GPS anomalies within a 20-minute window. The deviations ranged from 200 to 850 meters, appearing and disappearing without correlation to altitude, heading, or aircraft type. Air traffic control centers across the Baltic region began emergency coordination protocols. Flight plans were adjusted. Spacing between aircraft increased. Controllers shifted to backup navigation procedures that relied on ground-based radar and radio beacons, systems designed for the era before satellite navigation became the primary tool. The European Aviation Safety Agency activated its Crisis Coordination Center. What looked like scattered equipment failures was revealing itself as something coordinated. The GPS signals weren't disappearing, they were being subtly altered. The satellites themselves were functioning normally, transmitting their precise timing signals from orbit exactly as designed. But somewhere between those satellites and the receivers in aircraft cockpits, the signals were being intercepted, modified, and retransmitted with carefully calibrated errors. The manipulation was sophisticated enough to avoid triggering standard spoofing detection algorithms. It created just enough uncertainty to force pilots and controllers into backup procedures without causing immediate danger. Analysis teams began reconstructing the timeline. The geographic pattern showed a clear focus area, a corridor stretching from the Finnish coast across the Baltic Sea toward Poland, encompassing some of the busiest air routes in northern Europe. During peak morning operations, this corridor typically handled 240 aircraft simultaneously. The manipulation had been active for at least 7 hours before the pattern became visible. If it had continued undetected for another 12 hours, it would have intersected with afternoon peak traffic carrying an additional 180 flights. The technical teams identified the source architecture within 3 hours of full alert status. Multiple ground-based transmission sites had been positioned to create overlapping coverage zones. Each site broadcast GPS signals that mimicked legitimate satellite transmissions but introduced timing errors measured in microseconds. Small enough to seem like natural signal degradation, large enough to accumulate into dangerous position uncertainties. The sites operated in a coordinated pattern, activating and deactivating in rotation to avoid detection by standard monitoring systems. The vulnerability they'd exploited wasn't new. GPS signals are remarkably weak by the time they reach Earth's surface, about the same power as a standard light bulb viewed from 20,000 kilometers away. This makes them relatively easy to overpower with ground-based transmitters. What made this operation sophisticated was the precision of the spoofing. Rather than jamming or replacing the signals entirely, the system introduced barely perceptible errors that degraded navigation accuracy while maintaining the appearance of normal operation. If the morning operations had continued without intervention, the afternoon peak would have created critical conditions. With 420 aircraft operating across the affected zone under degraded navigation, the statistical probability of spacing violations would have increased by a factor of 7. Air traffic control systems would have been forced into emergency protocols designed for total GPS failure, procedures that reduce airspace capacity by 65% and require immediate diversion of flights that cannot be safely managed under backup navigation. Tallinn, Riga, and Vilnius airports would have exceeded their ground-based navigation capacity within 40 minutes. Helsinki and Warsaw would have followed within the hour. The cascading effects extended beyond aviation. The same GPS signals that guide aircraft also synchronize telecommunications networks, coordinate power grid operations, and provide timing references for financial transactions. Banking systems across the region relied on GPS-derived timestamps to sequence billions of euros in daily transactions. Mobile phone networks used GPS timing to coordinate their cell tower handoffs. Even emergency services depended on GPS for dispatch coordination and response routing. The manipulation had created a timing uncertainty of approximately 180 microseconds across affected systems. For most applications, this remained within operational tolerances, but several critical systems operated with much tighter margins. High-frequency trading platforms in Stockholm and Warsaw had begun experiencing transaction sequencing anomalies. Power grid synchronization systems had logged timing drift warnings. Emergency service dispatch software in 3 major cities had flagged coordinate inconsistencies that delayed response routing by an average of 4 minutes. The National Security Agency had been tracking the operation since Odo 2:30 UTC, nearly 2 hours before the first aircraft reported anomalies. The initial detection came not from aviation systems, but from a signals intelligence platform monitoring electromagnetic emissions across Northern Europe. The platform identified an unusual pattern of GPS frequency transmissions originating from locations that didn't correspond to known infrastructure. The signal characteristics matched previous spoofing operations, but the sophistication level exceeded anything in the current threat database. Within 90 minutes, NSA analysts had mapped the complete transmission network, identified the technical architecture, and begun coordinating with European partners on neutralization options. The challenge wasn't just stopping the spoofing. It was doing so without creating worse disruptions. Shutting down the false signals abruptly could cause navigation systems to snap back to true coordinates, creating sudden position jumps that might confuse automated safety systems. The transition had to be managed carefully. The countermeasure deployment began at 14:20 UTC. Specialized jamming systems activated across the affected zone, targeting the specific frequencies and modulation patterns used by the spoofing network. The jamming forced aircraft navigation systems to reject the corrupted signals and fall back to legitimate satellite data. The transition was coordinated with air traffic control to ensure that any temporary navigation uncertainties could be managed safely. Within 18 minutes, all affected aircraft had returned to accurate GPS navigation. Ground teams moved simultaneously to locate and disable the transmission sites. They found 12 installations positioned across a 400-kilometer arc. Each site consisted of commercial GPS simulator equipment modified for higher power output and mounted on commercial vehicles to enable rapid repositioning. The equipment wasn't particularly sophisticated. Most components were available through standard electronics suppliers. What made the operation dangerous was the coordination and the tactical understanding of how to exploit GPS vulnerabilities without triggering immediate detection. By 16 UTC, European airspace had returned to normal operations. The aviation authorities issued a notice to all pilots regarding potential residual GPS interference, and recommended enhanced cross-check procedures for the next 48 hours. Airlines reviewed their navigation backup protocols. Air traffic control centers updated their procedures for detecting and responding to coordinated spoofing events. The immediate crisis had been contained, but the vulnerability remained. The operation had demonstrated that GPS-dependent systems could be degraded without being destroyed. The attack didn't need to eliminate navigation capabilities entirely. It only needed to introduce enough uncertainty to force systems into degraded operating modes. For aviation, that meant reduced airspace capacity, increased delays, and heightened safety risks. For other infrastructure, it meant timing uncertainties that cascaded through interconnected systems in ways that were difficult to predict and harder to prevent. The technical investigations revealed additional disturbing details. The spoofing equipment had been in position for at least 6 days before activation, operating in a monitoring mode that gathered data about legitimate GPS signals and traffic patterns. This preparation period allowed the operators to calibrate their false signals for maximum effectiveness and minimum detectability. The activation timing, early morning on a weekday, was clearly chosen to impact maximum traffic during the day's second peak period. The geographic targeting showed strategic thinking. The Baltic Air Corridor serves as a critical link between European and Nordic aviation networks. Disrupting operations in this zone would affect not just regional flights but also intercontinental routes using the corridor as a transit path. A sustained degradation of just 12 hours would have forced the rerouting of approximately 340 long-haul flights, creating delays that would propagate through global aviation networks for days. The operation also highlighted the brittleness of backup navigation systems. While aircraft carry multiple navigation tools beyond GPS, air traffic control procedures and airspace design have increasingly optimized around GPS-based performance. The backup systems, radio beacons, inertial navigation, radar can maintain safety but cannot match the capacity and efficiency that GPS enables. A forced reversion to backup systems reduces the number of aircraft that can safely occupy a given airspace volume by more than half. European authorities and the NSA conducted extensive analysis of the transmission equipment and operational patterns. The technology fingerprints didn't match any previously documented spoofing operations, suggesting either a new capability or deliberate efforts to obscure attribution. The operation required expertise in GPS signal structure, knowledge of aviation procedures, and understanding of European airspace management. A combination that narrowed the possible source profiles but didn't provide definitive attribution. The incident triggered a comprehensive review of GPS dependency across critical infrastructure. Aviation authorities began accelerating programs to deploy alternative positioning systems and enhance detection capabilities for spoofing and jamming. Telecommunications providers reviewed their timing synchronization backup procedures. Power grid operators tested their ability to maintain coordination without GPS timing references. Financial systems began implementing additional verification layers for transaction sequencing. But the fundamental vulnerability persisted. GPS remains a civilian system, broadcasting unencrypted signals that any receiver can access and any transmitter can mimic. The satellites orbit 20,000 kilometers above Earth, making their signals inherently weak at ground level. Overpowering them requires relatively modest equipment and technical knowledge. The only effective defense is detection and rapid response, exactly what the Baltic operation had been designed to evade. The residual question wasn't whether another operation would be attempted. It was whether the next one would achieve the 12 hours of undetected operation that this one had been building toward. In that scenario, the afternoon peak traffic over the Baltic would have encountered navigation degradation just as weather systems moved in from the west. The combination of reduced capacity and deteriorating conditions would have forced emergency diversions across a region where backup airspace capacity was already stretched. The NSA continued monitoring electromagnetic emissions across the affected zone for weeks after the incident. Several suspicious signal patterns appeared and disappeared, suggesting that the operators were testing new approaches or gathering additional intelligence about defensive responses. European air defense systems increased their surveillance of GPS signal environments. Aviation authorities implemented new protocols for faster pattern recognition when navigation anomalies clustered geographically. Yet everyone involved understood the limitations of these measures. The next operation might use different frequencies, different modulation patterns, or different geographic targeting. It might activate more gradually to avoid triggering threshold-based detection. It might coordinate with other disruptions to create compound effects that overwhelmed response capabilities. The operators had demonstrated technical sophistication and operational patience, qualities that suggested they were learning from this event and preparing for future attempts. The Baltic incident remained classified for 6 months before details began emerging through European aviation safety reports. Even then, the full scope of the near miss and the NSA's role in the response stayed out of public discussion. Aviation authorities emphasized equipment improvements and procedural updates without detailing the coordinated spoofing operation that had prompted them. For the 420 pilots and flight crews who would have been operating in degraded conditions during the afternoon peak, the intervention represented a disruption they never knew had been averted. Their flights continued on schedule, guided by navigation systems that showed normal operation because specialized countermeasures had neutralized the threat before it reached critical threshold. The passengers aboard those aircraft, approximately 73,000 people traveling between European cities that day, remained unaware that their safety had depended on detection systems recognizing a pattern designed to stay invisible. The systems returned to normal. The airspace reopened to full capacity. The navigation signals resumed their quiet guidance of aircraft across the Baltic sky. But the vulnerability remained embedded in every GPS-dependent system across the region. A structural weakness waiting for the next exploitation attempt, the next test of how long coordinated degradation could persist before defensive systems recognized the pattern and responded. The question wasn't if another operation would come. It was whether the next detection would come fast enough to prevent the 12-hour window that would turn navigation uncertainty into cascading system failures across aviation, telecommunications, power infrastructure, and financial networks. All synchronized to the same satellites that had just proven themselves vulnerable to careful manipulation by operators patient enough to wait for their moment. The deeper analysis revealed operational details that heightened the concern. The spoofing sites had been positioned to create overlapping coverage zones with redundancy. If one site was detected and shut down, the others could compensate to maintain the degradation effect. This suggested the operators had anticipated defensive responses and built resilience into their architecture. The equipment placement also showed careful terrain analysis to maximize signal propagation while minimizing detection probability from ground-based monitoring stations. Technical forensics on the recovered transmission equipment showed additional sophistication. The systems had been configured to gradually increase their signal strength over the 7-hour period, starting at levels barely above the noise floor and slowly ramping up to more impactful levels. This progressive approach helped evade detection algorithms that looked for sudden changes in the signal environment. The timing algorithms embedded in the equipment indicated the operators had studied legitimate GPS satellite orbital patterns to synchronize their false signals with actual satellite positions, making the spoofed transmissions harder to distinguish from authentic ones. The coordination required between the 12 transmission sites pointed to a centralized command structure with real-time monitoring of the operation's effectiveness. Someone had been watching the impact develop, adjusting transmission parameters based on how aviation systems responded, and preparing to sustain the operation through the critical afternoon window. The fact that all sites activated and deactivated in precise synchronization suggested either hardwired connections or a dedicated communications network that had itself remained undetected throughout the operation. European telecommunications providers discovered their own vulnerability margins during post-incident analysis. The 180 microsecond timing uncertainty that GPS degradation had introduced came closer to critical thresholds than initially assessed. 4G and 5G networks require timing synchronization accurate to within 1 microsecond to prevent call drops and data corruption during handoffs between cell towers. The spoofing operation had consumed 180 of the roughly 250 microsecond safety margin these systems maintained. A slightly more aggressive timing attack could have pushed mobile networks into failure modes that would have affected 8.3 million subscribers across the affected region. Banking system reviews revealed similar proximity to failure thresholds. Electronic payment networks process 2.7 billion transactions daily across Northern Europe, with each transaction requiring precise timestamp sequencing to prevent duplicate processing or transaction loss. The GPS timing degradation had pushed several major payment processors within 90 microseconds of their fault tolerance limits. A sustained attack reaching 300 microsecond degradation would have forced emergency shutdown protocols that could have frozen card transactions for up to 6 hours, while backup timing systems synchronized. Power grid operators conducted extensive simulations of what would have occurred if the GPS degradation had persisted into evening peak demand periods. Electricity grids maintain stability by synchronizing alternating current frequency across vast geographic areas with precision measured in milliseconds. GPS provides the timing reference that enables this synchronization. The simulation results showed that timing errors exceeding 500 microseconds during peak demand could trigger protective circuit breakers designed to prevent equipment damage from frequency mismatches. In the worst-case scenario, this could have initiated rolling blackouts affecting 4.2 million households across 3 countries as grid operators deliberately shed load to prevent a larger cascade failure. The emergency services impact analysis produced the most sobering findings. Police, fire, and medical dispatch systems in 15 major cities relied on GPS coordinates for routing emergency vehicles and coordinating multi-unit responses. The navigation uncertainties introduced by the spoofing operation had already caused measurable delays, an average of 4 minutes that could mean the difference between life and death in cardiac arrest or trauma cases. Extended degradation would have forced dispatchers to revert to manual address lookup and voice-directed routing, a process that emergency service studies estimated would increase response times by an average of 8 minutes. For a region serving 12 million people, that delay translated to statistically predictable increases in preventable deaths. The NSA's detection capability had provided the critical margin. Without signals intelligence platforms monitoring electromagnetic emissions across the region, the spoofing operation would likely have remained undetected until aviation anomalies reached levels that forced immediate airspace restrictions. By that point, the afternoon peak would have been in progress, creating the exact crisis scenario the operators had designed. The 18-minute window between countermeasure deployment and complete neutralization represented the difference between a detected threat and a realized catastrophe. Intelligence analysts compiled behavioral profiles of the operators based on the technical evidence. The 6-day preparation period indicated patience and operational discipline. The choice to activate during low-visibility morning hours showed tactical awareness. The progressive signal strength ramping demonstrated technical sophistication. The geographic targeting of critical aviation corridors revealed strategic thinking. Together, these elements pointed to a capable adversary with resources, planning time, and specific objectives that extended beyond simple disruption. The operational debrief identified 3 critical lessons. First, GPS vulnerability represented a systemic weakness across multiple infrastructure sectors, not just an aviation problem. Second, sophisticated spoofing could evade detection long enough to create crisis conditions before defensive responses engaged. Third, the interconnection between GPS-dependent systems meant that cascading failures could propagate faster than defensive coordination could contain them. European governments initiated a classified infrastructure resilience program focused on reducing GPS dependency and improving spoofing detection. Aviation authorities accelerated deployment of multi-constellation navigation receivers that cross-reference GPS with European Galileo, Russian GLONASS, and Chinese Beidou satellites, making coordinated spoofing significantly more complex. Telecommunications providers began installing atomic clocks at critical network nodes to maintain timing synchronization even during GPS outages. Power grid operators expanded their network of independent timing sources, but these improvements required years of implementation and billions of euros in investment. In the interim, the vulnerability remained. The Baltic operation had proven that coordinated GPS manipulation could degrade multiple infrastructure sectors simultaneously while staying below detection thresholds. Long enough to approach cascade failure conditions, the systems remained stable. Navigation signals guided aircraft across their assigned routes. Telecommunications networks synchronized their handoffs. Power grids maintained their frequency coordination. Financial transactions processed in their microsecond sequences. Emergency vehicles responded to calls with GPS-calculated routing. Everything worked normally, until the moment it wouldn't.